Welcome to this fascinating exploration of the searing temperature smoke point paradox. This is a phenomenon that every chef encounters but few truly understand from a scientific perspective. Here's the paradox. When chefs sear meat at high temperatures, they often use temperatures that exceed the smoke point of their cooking oils. Yet the oil doesn't always burn or smoke excessively. How is this possible? A typical searing temperature for meat ranges from 200 to 260 degrees Celsius. This is quite hot. The smoke point of butter is about 150 degrees Celsius. Extra virgin olive oil has a smoke point around 190 degrees Celsius. So if we're searing at 230 degrees, but our oil smokes at 190, why doesn't it immediately burn? This is where the science gets interesting. When you place a piece of meat on a hot pan with oil, there's a thin layer of water on the meat's surface. This water plays a crucial role in protecting the oil from burning. The first key factor is that water acts as a temperature buffer. Let me explain the thermodynamics behind this. Water has a very high specific heat capacity compared to oil. This means it takes a lot of energy to raise water's temperature. The specific heat capacity of water is 4.18 kilojoules per kilogram Kelvin. For cooking oil, the specific heat capacity is about 2.0 kilojoules per kilogram Kelvin. Water requires more than twice the energy per degree of temperature rise. More importantly, water boils at 100 degrees Celsius at standard atmospheric pressure. This creates a temperature ceiling. When water evaporates, it absorbs a huge amount of energy, called the latent heat of vaporization. This is Q equals M times LV, where LV for water is 2,260 kilojoules per kilogram. All this energy goes into phase change rather than temperature increase. So as long as water is evaporating, the surface temperature stays close to 100 degrees, well below the oil's smoke point. Let's work through a numerical example to see just how much energy this water can absorb. Let's say there are 5 grams of water on the surface of our steak. That's 0.005 kilograms. The energy required to evaporate this water is 0.005 times 2,260, which equals 11.3 kilojoules. Now let's compare this to how much energy it would take to heat the oil to its smoke point. For 10 grams of oil heated from 150 to 190 degrees, that's a 40-degree rise. The energy is 0.01 times 2.0 times 40, which is only 0.8 kilojoules. Notice that evaporating the water requires about 14 times more energy than heating the oil past its smoke point. This enormous difference in energy requirements is why water provides such effective thermal protection for the oil during the initial searing phase. The second key factor involves the dynamics of the thin oil layer ITS. Not all of the oil reaches the smoke point simultaneously. The oil layer is very thin, typically less than a millimeter. Only the bottom layer in direct contact with the pan reaches extreme temperatures. There's a steep temperature gradient through the oil's thickness. The bottom might be at 230 degrees, while the top is much cooler. The temperature gradient is dT over dx, equal to the difference in temperature divided by the thickness d. Only the oil molecules right at the pan interface experience temperatures above the smoke point. The bulk of the oil remains cooler. The third key factor is that volatile compounds in the oil can burn off without propagating through the entire oil volume. Here's an important question. What actually causes the smoke when oil reaches its smoke point? The answer is the breakdown of fatty acids and other compounds. When triglycerides in oil are heated above the smoke point, they break down into glycerol and free fatty acids. Glycerol further decomposes at temperatures above 280 degrees Celsius to form acrolein, which is the visible smoke. In a thin oil layer, volatile breakdown products can escape into the air before accumulating. They don't saturate the bulk oil volume. The rate of heat transfer from the pan limits how quickly decomposition can occur. It's not instantaneous combustion of all the oil. Let's develop a simple mathematical model to understand the heat transfer dynamics during searing. Fourier's law of heat conduction tells us that the heat flux Q equals negative K times dt over dx, where K is thermal conductivity. For cooking oil, the thermal conductivity K is approximately 0.17 watts per meter Kelvin. Notice that oil is actually a relatively poor thermal conductor. This means heat doesn't spread through it very quickly. If we have a 1 millimeter thick oil layer with a 130 degree temperature difference, the heat flux is about 22, 100 watts per square meter. Now let's calculate the time scale for the oil layer to reach thermal equilibrium. The thermal diffusion timescale tau is approximately rho CD squared over alpha, where alpha is thermal diffusivity. For oil, thermal diffusivity alpha is K over RHOC, approximately 9 times 10 to the negative 8 square meters per second. For a 1 millimeter layer, tau is about 0.01 seconds. This is quite fast, but during this time water evaporation is occurring. There's an important connection to the Maillard reaction that helps explain why searing works so well. The Maillard reaction, which creates the delicious browned crust on meat, occurs optimally between 140 and 165 degrees Celsius. Notice this temperature range is actually below the smoke point of most cooking oils, so the chemistry we want is happening in a safe temperature zone. During searing, we create a temperature gradient. The crust forms at Maillard temperatures while the interior stays much cooler and the oil is protected by evaporating water. Let's discuss the practical implications of this paradox for actual cooking techniques. First implication: you should pat meat dry before searing, but some surface moisture is actually beneficial for temperature regulation. Too much water means the surface stays at 100 degrees, and you get steaming instead of searing. No Maillard reaction occurs. But too little water means you lose the thermal buffer and risk oil breakdown and excessive smoke. Second implication: choose oils with smoke points that provide some safety margin, but don't obsess over exact temperatures. Refined oils typically have higher smoke points than unrefined oils. Refined avocado oil can reach 270 degrees Celsius. Third implication: control your pan temperature. Preheating is important, but you don't need maximum heat. A good rule of thumb is to sear at about 20 to 40 degrees above the oil's smoke point. The water buffer gives you this margin of safety. The material and thermal mass of your pan also play crucial roles in this paradox. Cast iron pans have very high thermal mass. When you place cold meat on them, they don't lose much temperature. Heat capacity C equals mass times specific heat capacity. A heavy cast iron pan might have a heat capacity of 1000 joules per Kelvin. This high thermal mass maintains a consistent high temperature even as moisture evaporates, enabling good searing. Stainless steel has lower thermal mass and conductivity, so you need to preheat it thoroughly and use slightly more oil. There's an advanced phenomenon called the Leidenfrost effect that can sometimes occur during high-temperature cooking. When a pan is extremely hot, water droplets can levitate on a layer of their own vapor. This is the Leidenfrost effect. The Leidenfrost temperature for water is approximately 200 to 300 degrees Celsius, right in the searing range. When the Leidenfrost effect occurs, it creates an insulating vapor layer that actually slows heat transfer to the meat. This is generally undesirable for searing. For optimal searing, you want vigorous boiling and evaporation, not Leidenfrost levitation. This means your pan shouldn't be too hot. Scientists have actually measured these temperature dynamics in real cooking scenarios. Let me share some experimental findings. Using infrared cameras, researchers have observed that the oil-meat interface rarely exceeds 180 degrees Celsius during the first 30 seconds of searing. This is true even when the pan surface is measured at 250 degrees. The evaporating water keeps the interface cooler. After most surface water evaporates, typically after 45 to 60 seconds, the oil temperature can rise very quickly, sometimes reaching 200 degrees in just 10 more seconds. This rapid temperature rise after water depletion explains why timing is so critical. Flip too late and you risk burning the oil and creating bitter flavors. This graph shows a typical temperature profile. The oil stays below the smoke point during initial searing, then rises after water depletes around 60 seconds. Let's examine the chemistry of oil degradation from a kinetics perspective. The rate of oil breakdown reactions follows Arrhenius kinetics, meaning reaction rate increases exponentially with temperature. The rate constant K equals A times e to the negative EA over RT, where EA is activation energy, R is the gas constant, and T is absolute temperature. For oil oxidation reactions, the activation energy is typically 80 to 120 kilojoules per mole. The ratio of reaction rates at 230 versus 190 degrees Celsius can be calculated. Let's use 463 and 503 Kelvin. The reaction rate at 230 degrees is about 2.5 to 4 times faster than at 190 degrees. Significant but not catastrophic for short exposure times. This tells us that exposure duration matters as much as peak temperature. Brief spikes above smoke point cause minimal degradation. Many cooking oils contain natural or added antioxidants that provide additional protection during high heat cooking. Vitamin E, also called tocopherol, is a natural antioxidant present in many oils. It scavenges free radicals formed during heating. Extra virgin olive oil contains polyphenols that help prevent oxidative degradation, even above its nominal smoke point. This antioxidant protection is why some oils, like extra virgin olive oil, perform better at high temperatures than their smoke points would suggest. An important realization is that smoke point is not a hard threshold where oil instantly becomes unusable. The smoke point represents the temperature where visible smoke begins to form, but it's really a gradual transition zone, not a sharp cutoff. Oil composition varies somewhat between bottles and brands. The smoke point can vary by plus or minus 10 degrees Celsius. The amount of free fatty acids already present in the oil affects its smoke point. Refined oils have fewer free fatty acids and higher smoke points. Each time you heat oil, you create more free fatty acids, which lowers the smoke point for subsequent uses. This is why you shouldn't reuse frying oil indefinitely. Let me address some common misconceptions about high heat cooking and oil smoke points. Misconception 1. Any visible smoke means the oil is burning and the food is ruined. Not necessarily. Brief, light smoke is normal and acceptable. Misconception 2. You should always use the oil with the highest smoke point. Actually, flavor matters too. Butter and olive oil add wonderful taste. Misconception 3. The smoke point is a fixed property. As we discussed, it varies with oil quality, age, and previous heating history. Let's do a complete energy balance analysis for a typical searing scenario to tie everything together. Consider searing a 200-gram steak in a cast iron pan at 230 degrees Celsius using 10 grams of oil with a smoke point of 190 degrees. Assume there are 3 grams of water on the steak surface after patting dry. Energy for water evaporation. 3 grams times 2,260 kilojoules per kilogram equals 6,780 joules. Energy to heat the surface layer of meat by 20 degrees, using specific heat 3.5 kilojoules per kilogram Kelvin, 14,000 joules. Total energy that must be supplied, about 2,780 joules or 20.8 kilojoules. If this energy is delivered over 30 seconds, that's about 690 watts of power transfer. Power equals energy over time. 780 divided by 30 equals approximately 690 watts. A typical gas burner provides 2,000 to 3,000 watts, so 690 watts is easily achievable. This shows the energy balance is quite feasible. During this 30-second phase while water is evaporating, the oil temperature remains below its smoke point, protected by the thermal buffer. Let's summarize how we've resolved this apparent paradox. First, water on the meat surface provides crucial thermal buffering through its high heat capacity and latent heat of vaporization. Second, only a very thin layer of oil at the pan interface reaches extreme temperatures. The bulk oil remains cooler. Third, volatile breakdown products can escape from the thin oil layer before accumulating to dangerous levels. Fourth, the kinetics of heat transfer and chemical reactions limit how fast oil degradation can occur. All of this creates a brief window of opportunity, typically 30 to 90 seconds, during which excellent searing can occur without significant oil degradation. Based on this scientific understanding, here are practical recommendations. Use medium-high heat rather than maximum heat. You want around 220 to 240 degrees Celsius, not 300. Pack meat dry to remove excess water, but some moisture is beneficial. Don't desiccate the surface. Choose oils with smoke points about 20 to 40 degrees below your intended searing temperature. This gives safety margin. Use enough oil to thinly coat the pan surface. Too little oil creates dry spots that can burn. Don't leave meat unattended. The transition from protected searing to oil degradation happens quickly once water depletes. For optimal crust formation, flip the meat right when the first wisp of smoke appears. This is your signal that water is depleted. This paradox illustrates important principles that apply throughout food science. Phase transitions like evaporation create temperature plateaus that protect other components. This principle appears in many cooking techniques. Thermal gradients through thin layers allow for simultaneous hot and cool zones. This is key to many cooking methods. Reaction kinetics matter as much as equilibrium thermodynamics. Short exposure times prevent unwanted reactions even at high temperatures. Ultimately, cooking is applied chemistry and physics. Understanding these principles allows for better control and more consistent results. The searing temperature smoke point paradox beautifully demonstrates how multiple physical and chemical phenomena interact during cooking. Scientific analysis explains why traditional cooking techniques that were developed empirically actually work so well. Understanding the underlying science allows chefs to innovate beyond traditional methods and to troubleshoot when things go wrong. There's a special joy in recognizing that delicious food is the product of elegant physics and chemistry happening right in your kitchen.